Welcome, dear colleagues, dear students, ladies and gentlemen, for this very first colloquium of the Department of Physics. As many of you will know, some of our PhD students launched the idea some time ago to organize these colloquia. And the idea is to invite a prominent speaker from outside of our department to enlighten us on some new developments in the field of physics, which are perhaps a little bit or even very much out of our own specific specialties. It is a very great pleasure to have with us today Professor Conny Aerts from the University of Leuven and University of Nijmegen to bring us this very first colloquium in a series which will follow. As a matter of fact, she just told me that she started her career in mathematics, not really in physics, in this very specific room. I will pass on the word to Nick Frelst, who will give a proper introduction. Our speaker for today. Just let me invite you to the reception which will follow this colloquium, where we will have the possibility to meet the speaker and discuss matters a little bit further. Nick, please.
So, thank you very much for these first words. So, it's Nick van den Broek. So, I have very little to add, except that I want to remind you guys of one thing. Even though that those few PhD students that started the idea, we are the organizing committee, this colloquium is as much yours as it is ours. So therefore I want to remind you all that we are very keen to keep getting your comments, getting your suggestions. And I want to thank you all for those suggestions that we have gotten so far, because they've resulted in 3 very high level, very top-notch speakers for this year. And I want to pass 2 dates already, except for today, that you also need to write down right now. So that's February the 20th and March the 31st. And, of course, today, we have our opening edition by Professor Conny Aerts. And Professor Aerts enjoyed, as Professor Dirks already told you, she started here with a mathematical education. And after that, she continued her PhD in Leuven. Now there, she very quickly became one of the pioneers of a brand new research domain, namely Asteroseismology, about which I am sure she will explain a lot more today. She received the ERC Advanced Grant in 2008 from the European Research Council for her research, and this allowed her to pursue and further enhance that field and allowed her research group to develop more tools, which was called Prosperity, the grant, which was a huge success because in 2012 she received for that the very prestigious Franck Prize, making her the very first woman to receive it in the field of exact science. So without further ado, I would like to ask your undivided attention to Professor Conny Aerts and the department of Asteroseismology, the revolution in stellar physics.
Thanks a lot for this introduction, and indeed, nice to be back home. After 30 years, that's a bit scary, but that's reality. And so, well, as already said, I started my career as a mathematics student here and then moved on to astrophysics. And so it's not a coincidence that the talk I'm going to give you today is about asteroseismology, which is a quite mathematical branch in stellar physics. So in that sense, you raised me quite well. Thank you for that. Asteroseismology is a brand new field. It is a field in astrophysics, which is probably not the main focus of the physics research here. So for that reason, I will first of all try to explain to you what it is, why do we care about it, How does it work? So that you all can do this in practice when you go home after this seminar. If not, you can ask for a little help, but still. And then applications and where it stands today, and what we're going to do tomorrow, let's say. Well, the motivation of our research is that we want to understand the universe. That's the grand scheme, grand picture. And if we want to do that, we need to understand how stars work, because these are the building blocks of the universe. Now, we know fairly well how stars get born out of molecular clouds. They get born together in clusters. Here the Pleiades, which you can see by eye if you know where to look, and if it's better than today. We are in a galaxy, like this one, schematically shown. And we know that stars evolve differently depending on their birth mass. So this sets the whole scenery of their life. And so basically we have two big paths, one could say. A small or a star like the Sun, which has masses typically between, let's say, 1 and 8 solar masses, what it's in this cartoon called a small star, that will evolve after its nuclear fusion has ended in its core to become a red giant, will expel its matter in a slow wind and will end or die quietly as a white dwarf. That's the whole evolution of stars like the Sun. If we have stars that are born with more mass, typically above 8 to 9 times the mass of the present Sun, then the evolution is a bit different, much faster, and so these stars will evolve towards supergiants and will explode at a certain point in their life as a supernova. And a supernova can have two different remnants, either a neutron star, depending on the mass that is left over after the explosion, or a black hole if the mass that is remaining is above twice solar masses typically. So we know fairly well how stars evolve, how they live their life. But if we are very honest, then our stellar models are still quite limited today. As I tend to call it, the devil is in the details, because we don't really know how the interior mixing processes of stars happen. We can't look inside a star. That's, by the way, the hardest thing to do in terms of observational astronomy. We can look farther and farther to outer galaxies and to the limit of the universe, but we can't look inside the Sun. We can't look inside stars because the stellar gas is opaque. So you have this gaseous sphere and you see the light emitted through its surface. And that's what we have to do as experimentators, one could say. That's the signal we get, and all we can do about it is use that, because I can't travel towards the inner regions of the star. So how do stars rotate internally? Do they have magnetic fields internally? Well, we certainly know that the Sun has magnetic fields, and this can give rise to quite spectacular phenomena, which you can see sometimes. But frankly, for the life of the Sun, it doesn't matter. It matters for us here on Earth, and we can have electromagnetic storms. That's annoying, and we want to protect ourselves against that. But for the life and evolution of the Sun, the magnetic field is not strong enough to play a big role. And so, in general, we don't know how matter mixes. And if you don't know how things rotate, then you have a lack of knowledge of the most important mixing process. I always compare that with milk to pour in your coffee. You don't want to wait until it's completely mixed, because then the coffee is cold. It's not very nice to drink anymore. You give angular momentum, right, with a spoon. And so as soon as you have rotation, you have very efficient mixing. And what we can study from stars is their surface rotation. We know how the Sun rotates on its surface. We can just measure it. You can even do that experiment yourself, or you can just be clever and use your eyes, protected by these glasses. And then you can deduce the surface rotation rate of the Sun. It's about 26 days, in case you didn't know that we have a lack of culture, right? But that doesn't say how the sun rotates in its interior, and that's where the mixing processes are important, because in the interior is where all the action lies in terms of nuclear fusion. So stars have nuclear fusion in the sense that they transform hydrogen into helium in their core, and it's this inner core region where the nuclear fusion takes place that determines how the star evolves along these two broad paths, but we would need to know how the mixing happens inside. So we need a tool to look inside stars. And that's the beauty of asteroseismology, which I've schematically presented here in this plot. And people always ask me, you made a typo in your typo, it has to be asteroseismology. No, it is not, because this is derived from Greek, and there aster means star, seismos means oscillation, and logos means that you do some kind of reasoning. So what we're going to do is use star quakes, if you like, and do seismology of stars, just as seismologists of Earth use earthquakes to probe the core of the Earth. I can't drill a hole here to understand and study how the core of our planet looks like, but we can do it by earthquakes, either natural ones or invoked earthquakes. We do the same, but then for stars. Only I can't direct the quakes on a star. We have to do with what they offer us. But stars have quakes. They have oscillations, if you prefer that word. The sun also has that. You can't see that by eye, because your eye is a magnificent detector, but not good enough to see these tiny solar quakes, let's say. They are there, and they have a consequence on the luminosity, on the light that is received from the sun. Typically, the variations that are connected to these quakes of the solar surface are expressed in parts per million. And that's not within reach of your eyes. You need a better detector for that, but the principle is there. So we have these quakes on stars, they have seismic activity, they do that periodically, and in their interior, where we cannot see, these quakes behave as sound waves. And that's what you see here in the upper graph. You see various sound waves plotted here schematically. You see the red one. That one probes the outer layers of this hypothetical star. And that blue one here goes all through the center. Me as a seismologist, I strongly prefer the blue ones, because I want to know what's going on in the interior, and that's probed by these waves, let's say. Now the green and the yellow are placed here and are multiplied often here to give you an illustration without using the mathematical descriptions of what we do in practice. We try to observe and detect the quakes, that's one thing, that's the observational part, I will come back to that. But then we can make an estimate of the frequency that we detect in the seismic activity about the yellow, let's say, and green sound waves. The yellow probes this region, and the green goes a bit deeper. So as soon as we have two quakes, whose frequency we can determine very well, these frequencies are determined by the inner physical properties of that gas, its pressure, its density, its temperature. If we subtract these frequencies from each other, then we learn something about the physical conditions of the tiny little layer that's green here and not yellow. And so if we can do that with many seismic oscillations, we build up the star layer by layer. That's in fact what we are trying to do. And so that gives us a handle on the interior physics, which is far better than just using the surface properties of the star. I always compare this with music, if I give popular talks on this subject. Here's seismic activity. So time runs here, and this is a quantity, let's say the luminosity. And if you have quakes, then this changes a bit. And you can determine the frequencies with these changes. I learned that here, frequency analysis, yes. And it's error propagation, first 6 weeks of my mathematics studies, because here in Antwerp, mathematicians have to go to the lab. I don't know if that's still the case now. We had to do that. I didn't like it, but I learned a lot. Okay? And so you have these variations due to the quakes, and depending on the frequency that you measure in such a signal, you can determine if it is a big violin, a small violin, or a contrabass, let's say. Yeah? You can do these experiments with flutes, with very small kids. You always get the correct answer, because by hearing the frequency of the sound waves, you immediately can connect the extent of the instrument. Right? For me, a star is just a musical instrument, only I can't detect the sound waves by listening, because there's vacuum between the stars and us. So we have to determine the frequencies in another way, and how we do that is by following either the luminosity changes that we see on the surface due to these oscillations, or the brightness changes, velocity, etc. So we need a refined instrument that can measure parts per million in brightness, let's say, and then we can determine frequencies. Here are data, real data from the recent Kepler satellite. So here's relative intensity as a function of time, and time here is expressed in days, for 4 stars whose size is schematically shown here. And here you see the frequency of the seismic activity is much higher than here when you have a big star, a giant star, where the variations are much slower. It's normal, these sound waves have to travel all the way through the star. If your star is bigger, it takes longer, right? And so it's slower. So what do we do in practice? We measure stars, their surface brightness variations. We do that from space these days. We put ourselves into Fourier space. You are good at that, you're all raised like that. That's easy. Bachelor level type exercises, right? You have the frequencies of the oscillations, and since we're dealing with spherically symmetric stars, gaseous bodies, the eigenmodes of these quakes can be described by spherical harmonics. And so each spherical harmonic is characterized by a degree and an azimuthal number. So that I learned in my first year here. In the mathematics classes, and then the n value here is the overtone of the oscillation mode. That's like a guitar string, you know. A musical player knows perfectly well how to play it in the basic tone, or in higher harmonics, depending on where he or she puts his fingers. So these values, L, M, and N, determine the eigenmode of each oscillation mode, and they belong to a specific frequency. And then we try to model, we do mathematical modeling of these measured frequencies and their identified spherical wave numbers, let's say. Now, as you also know, again, think of music. If I add rotation, I want to measure rotation inside stars, because that is how I can improve my theory of stellar evolution. If you have rotation in your gas, it will shift the frequencies of the sound waves. And so this shift can be computed once you know what kind of oscillation frequency you would have in case that there would be no rotation. So all the stellar models up until a few years ago assumed that there was either no rotation inside the star, or that the rotation is rigid, so that all layers have the same rotation frequency. You have to do something, right? So let's take the simplest until we find some evidence, experimental evidence, that this is too simple. And that's the stage we're in right now. And so this shift of the frequencies is directly connected with the internal rotation rate that we would like to find out for stars. So that's one of the things that asteroseismology can do for us. So in practice, this is a quite theoretical, mathematical scheme, let's say. What do we do? On the one hand, we have observations, and I will show some more later. We do frequency analysis. We label the modes, if we can. We have to do that, else we are stuck. And that gives us the observed oscillation properties of the star. I want as many modes as possible, just like seismometers here. Well, seismologists want to have as many frequencies of earthquakes as possible, because remember, we're doing frequency differences, and the more differences I can make, the more internal layers I can probe, let's say, okay? And on the theory side, well, we have theoretical stellar models. We have them as we believe they are best. How do we construct these? It's very simple. You use the basic laws of physics, conservation of mass, momentum, and energy. And then all sorts of microphysics that we put in, where we combine information from nuclear physics, because we have nuclear reactions, we do thermodynamics, we do mechanics, and all that we put together to make a model of a star. That is dependent on the chemistry, which is indicated as XZ here. So the chemistry of a star has dominantly hydrogen, helium, and then there's metals for a few percent. We call that all the rest, you know. The chemistry of a star is quite simple compared to other bodies in nature, let's say. And as I said, the birth mass, this big M here, is one of the parameters, and tau is the age of the star. Something that is very hard to determine. By just measuring surface properties of stars, it's really hard to determine how old it is. Why is that? All the action is in the core. That's where the nuclear reactor is. That's where the heavy elements are produced by transforming hydrogen to helium, later on helium to carbon, then carbon to oxygen, and so on. But we can't see that. And so we need to find a way to determine stellar ages. And then there are two mixing parameters here. As I said, we don't really know how mixing works. And you can have two types of basic mixings. One is convective motion that occurs inside a star. That's the same as a boiling water kettle, let's say. If you put on your stove, the water is horizontal, but you increase the heating and it has to be transported, and at a point you reach a temperature that it starts to boil and you have bubbling bells. Inside stars there are regions with bubbling gas bells, depending on how much heat you have to get rid of, so to speak. If you have convection, then you have very efficient mixing. In your water kettle, if you drop an ink particle, it's immediately blue. While if you do that in the kettle that doesn't boil, doesn't mix efficiently. And if it mixes efficiently in a star, it means you bring new fuel into the nuclear reactor. So that determines how the life evolves, because that determines how long you can do nuclear fusion. And so then these parameters are unknown to us, and we try to estimate them. We put all these equations of physics, we put them in a computer code. That's where the informatics comes into play. We choose clever boundary conditions, and we solve the set of equations numerically. And this then gives you a model of the star in equilibrium. Then you turn on the seismic activity, which is a perturbation that you invoke, and you create deviations from symmetry. We assume linear perturbations. That's very well fulfilled for these quakes. These are small disturbances that we have. And you get a theoretical pulsation spectrum of your star, but you don't really know which of the eigenmodes are excited and which are not. And that's we can only do by coupling to the observational properties. At first instance, with a very simplistic comparison. Okay? So that's what we do in practice. We couple stellar modeling to time series analysis. Now, we have learned this from the sun. The sun has solar quakes, if you like. And then the field is called helioseismology. These oscillations have been discovered in the late 60s, 1960s, early 70s. And solar networks have been put on the Earth to observe and detect these oscillations with high precision. And that has really brought the field of helioseismology a long way, typically, let's say 20 years ago. What you see here is a power spectrum where the frequency is expressed in microhertz, and all these maxima here are the solar oscillation frequencies. Now, maybe it's not so clear for you, but this is a graph where you see a maximum, clear maximum, without being an expert in time series analysis. The solar oscillation quakes peak here near 3000 microhertz. If you invert that, if you're not a Fourier person like I am, but a more daily time person, that's 5 minutes. So the quakes go up and down on the solar surface for a few minutes, and then they're back in their equilibrium position. And the quakes are continuously going on in the interior of the sun. And you see many quakes. Each maximum here is one seismic mode. Okay? And you also see, I think, without being an expert, that this is not a random occurrence of seismic waves. These are the eigen frequencies of the sun, and there is a clear pattern here. We tend to call that the frequency of maximum power, and then this difference here is always almost equal. That's because the sun has nice acoustic modes in, I'm a mathematician, the asymptotic regime of high frequencies. And this frequency separation is directly connected to the interior sound speed of the sun. So by interpreting each and every of these frequencies, by doing mathematical modeling, we can compute, sort of invert the interior sound speed of the sun, and as you know very well, that's connected to the interior pressure and density and temperature. To a good approximation, stars like the sun fulfill the ideal gas law. So that's not so hard to do that. Okay? Now the sun also rotates, we know that because we see its surface rotating. But we can also deduce that from this spectrum. If I would blow it up and do a very detailed frequency analysis, it would cost several weeks to do that in total. You would see splitting of the oscillation mode frequencies due to the rotation. And by reconstructing that integral that was on my previous slide, you can then deduce the rotation frequency, and that's this color plot that you see here. And since it is in different colors, it means that the rotation is non-rigid. If there would be one rotation, then it would be in the same color coding. Yeah? And so you see that the rotation frequency here is lower than the rotation frequency here, and for the periods it's then the other way around. Okay? And so that means, here you see the curves as a function of the interior of the sun. Here's the surface. Here we're halfway through the star. And these curves tell you that the rotation is quite differential, but at a certain moment, at a certain depth, here it's almost constant. This was not what people had expected, because it was thought that the interior of the sun would have a magnetic field and a dynamo created there, and it's exactly the opposite. It's a differentially rotating star in its outer layers up until, let's say, 72%. And so in these layers, you automatically have better mixing, because again, if there is rotation, you have an effect of matter that mixes, but that's not where the nuclear fusion happens for the sun, because that's in its core. Yeah? Now the problem is for the sun that we can't go further here. That's really annoying. You know, it blocks our knowledge of the core of the sun. We can go a bit further here these days, up until, let's say, 0.2, but not to its core. So we don't really know how our own sun, our star, rotates in its core. That's not very good as basic knowledge. The good news is that we know it now for other stars. That's quite amazing. And then we can do some kind of backtracking. Yeah? We are now in the middle of the life of the sun, more or less, as you know. Maybe not, but for your general culture that's important. Because we will enter a stage of what we call, well, I call it gradual warming, to avoid global warming. That means something different. But none of the two are pleasant. And to comfort you, the sun is not going to be the showstopper, because this gradual warming happens in billions of years from now. So that's nothing to be worried about. Anyway, the Sun is just one very simple, for me a bit boring star, because I'm a massive star fan. I like supernova explosions and so on. And so it will not explode. What do? We want to test the results of helioseismology for other stars, and astronomers, they use this famous Hertzsprung-Russell diagram, where you have here a measure of the surface temperature from cold to hot, and on the y-axis the luminosity of the star. And all these ellipses here, these are all star positions where when the star enters there during its life in this position, then it has seismic activity. We have monitored that. That's just a matter of measurements and making inventories. Stars get born on this dotted line here, and then they evolve, and to our best knowledge, the stars evolve on these evolutionary tracks that you see here as full lines. And so what we are trying to do is test that from seismology and make it better, let's say. For massive stars, the interior reactor that you see schematically here is in an area where there is immense nuclear energy production, and there is a lot of energy that has to be transported, and so it boils there, so to speak. So the mixing in a massive star, and when I say massive, it's each time, born with several times the mass of the Sun. This boiling kettle here, we want to understand how much of the matter is in the boiling areas, how much convection mixing we have, because that determines how long the star lives. So that's one of the unknowns that we try to find out. How do we do that? Well, we are very happy these days because there were 2 space missions that helped us greatly, and that's why this research domain has really started. This is the CORO mission. CORO stands for Convection and Rotation of Stars. It was operational in these years. And the NASA Kepler mission is still ongoing now, even though I put here 2013. Well, the mission was designed to last for 4 years. Its main goal was to hunt for exoplanets. That's another talk, I will not cover it. And it sort of broke down after 4 years, so that was what the engineers had promised us. That's perfect. The instrument didn't break down, but 2 of the 4 gyroscopes broke down. So what do you want to do if you want to study seismic activity? You put your telescope in space because the Earth atmosphere is really annoying. It also has these fluctuations. We don't want them. So we put a space mission on top of that. And then you stare at stars, as many stars as possible in one shot. And you stare at them during a long time, because we want to do a frequency analysis, and I want to have a long time series. And so here you see such a time series of a coral star, brightness variation as a function of time. And you see that that star indeed has seismic activity, beautiful oscillations. You add up various sine waves and you get this beating pattern. And in frequency space you nicely flip that into delta Dirac peaks. And these are your eigenfrequencies. This is a Kepler measured star. So CORO did that when staring at the sky, a certain field for 5 months, and had one measurement every 32 seconds for some bright stars and every quarter of an hour for fainter stars. We express the brightness of a star in magnitudes. Astronomers are weirdos in many senses, but particularly in units. We do not use SI units, even though we are raised like that, and even I was already raised in SI units here. But anyway, we do it differently, and that's because the star's brightness works logarithmically, and so that's one of the reasons. So we use magnitudes. You see here a beautiful oscillation pattern, seismic activity of a star that was followed by Kepler, and Kepler stared at the field not during 5 months, but during 4 years. So we get a very high precision frequency measurement for very many stars. And that's what we have been analyzing the past 5 years. And that's where my European funds were very welcome, because this is just work power that I needed. Yeah? Once the mission is launched, the risk is gone. So high risk, high gain is what the ERC promotes. Huh? High risk was a satellite, it could have exploded, no data. High gain is the very many stars that we could analyze up until today. Here are two stars. These two stars are in a binary, and you have power as a function of frequency, and you see again something very similar than what I showed before for the Sun. Huh? So these are almost copies of the Sun. The nice thing is that they are a binary. So these are two stars revolving each other in a wide orbit, Kepler orbit. That's easy to describe. And well, you see also again maximum power almost here and almost here, bit lower frequency than the Sun. The Sun was at 3000 microhertz. Yeah? So if the frequency is a bit lower, it means the star is a bit bigger because the period is a bit longer, right? And so the musical instrument is a bit bigger. It's as simple as that. So as soon as you have your light curve and you have your Fourier transform, you can immediately tell how big the star is with respect to the Sun. That's our calibrator, so to speak. And so then you can do all sorts of analysis by what we call a shell diagram. So what is here? Here is frequency modulo this large frequency spacing that I showed in the Sun, which is very regular. Yeah? Then you cut your time series and you stack it on top of each other. It's what we call the shell diagram, and you see the different types of modes. Huh? 4 ridges here. They belong to 4 types of degree of the spherical harmonic. You have a YLM, and for L equals 0 you have a ridge here. For L equal 1, for L equal 2 is here again, and L equal 3. Yeah. So we can recognize this pattern. We do some kind of pattern recognition if you want to speak language of a statistician, and that's the labeling of the spherical harmonics connected to the frequency. Once you have that, you do your modeling, and that's the way it works. Okay? And then you can get all sorts of information of mixing. Now, one surprise to us, which we didn't anticipate it, was this a shell diagram of a red giant star. So the Sun, when it has no longer any hydrogen in its core, it will have to stop, it will have to solve an energy crisis. Yeah? Because the nuclear fusion, which transforms hydrogen into helium, well, if there is no hydrogen, there is no fuel, right? So your fuel tank is empty, so to speak, because all the hydrogen has been transformed into helium. And to burn helium, you need another reactor. You need a reactor where the temperature has to increase with a factor 10. Yeah? Nuclear physicists among you know perfectly well how that goes. You do a triple alpha reaction, and then you again can burn and live. Huh? But, you know, there's an intermediate period when the star has an energy crisis. Again, for the Sun, this will happen in very many years, so no worry. But at that point, the star will have to make its core hotter to survive. So the core will shrink, and conservation of angular momentum then says the outer layers will blow up, and you make what we call a red giant star. Okay? Red giant stars, seismic activity, quakes. We know how the period should work. Huh? Bigger star, lower frequencies, harder to find in the data because you have to wait longer because the beating pattern is long. Huh? That's fine if you have a space mission doing that, but here there is a ridge of L equal 2 modes, here L equals 0, and this was supposed to be a ridge, one ridge of L equal 1, so dipole modes. Now there is no ridge, and my student was Paul Beck, remember that very well, came and have a discussion with me because he was convinced that he had a computer problem in the sense that his Fourier transform code must have had an error because he didn't get this beautiful shell diagram here for the L equal 1. But I know that he did a great job because here are beautiful ridges. And so these are dipole modes that are what we call mixed modes. Yeah? So when I showed you in the beginning this cartoon-like illustration of how we work, we have sound waves inside the star. These are mainly caused by pressure fluctuations. You know very well how sound waves work. But you can also have oscillations whose dominantly restoring force is buoyancy. That's another family of modes. These are called gravity modes. These are much more interesting for seismologists because they probe the inner regions. That's that purple arrow that I showed in the beginning. Okay? And so these red giants, they now turn out to have modes. I'll click on this, I'm not sure if it will work. Yeah? That are mixed modes. So what you see here is the outer surface layers have these pressure modes, dominantly driven by the pressure force, but if you zoom into the interior, they behave like gravity modes. If you find that too abstract, think of the ocean waves. These are surface waves on the ocean that are, that mainly have horizontal motion. These are typically gravity waves. And so from that we can probe the inner regions much better. And that's what you see in this diagram below here. Here is a graph of the frequency separation, so that's that regular pattern that we measure, and regular period spacing that occurs when you have modes that are dominantly driven by buoyancy. And all these stars here are stars that have been measured by the Kepler satellites. And for all of those, you immediately grasp what their radius is, what their mass is, because we can use that from scaling, and we want to know if these can help us to derive some information on rotation. For that, we have to see how the modes are split. And so these dipole modes is an L equal 1. Think of your spherical harmonics. YLM. If L equals 1, then M can have 3 values, either -1, either 0, or +1. Right? That's how it goes. So what happens? What does rotation do? Instead of one frequency, in the case where the layers where these modes probe do not rotate, you get triplets. And the splitting value of the triplets tells you how fast rotation is there locally. And so that we can do for these red giants. And this has been done, I'll skip this and move to this diagram. This has been done for very many stars, each of those. So what we tend to do is put in here the effective temperature, and we replace the classical vertical diagram by the frequency separation, which we can measure for all stars that have seismic activity. You see all these gray symbols here. Here are the birth masses, and these are the evolutionary tracks. And here is our sun. Luckily, it's on the 1.0 solar mass track. That's our calibrator, right? And so these stars are evolved. They have gone off to a phase where they have no central hydrogen nuclear burning anymore, because there is no hydrogen anymore. And so what you see here is a deduction of their internal rotation rate at the core as a function of their gravity. And there are 6 stars that are highlighted here. And the difference between the core frequency and the envelope frequency is increasing as they evolve. The stars become bigger and bigger and bigger. The core becomes smaller and smaller and smaller and spin up more rapidly. That's the ice skater principle. Okay? Our models have no way of explaining that, because they used to have either no rotation in the interior, or rigid rotation, or local conservation of angular momentum. Before we had seismology, these were the basic 3 suggestions, and the data tell us we are a factor 100 wrong, and we are trying to work hard to solve that. You see that in these diagrams. So here's a graph of the rotation frequency as a function of that inside the star. And so we have to try other mechanisms. We are trying to put in a magnetic field now, because we lack coupling clearly between the core and the envelope of the star. It's too slow. The theory had predicted, if we use local angular momentum conservation, that the difference would be a factor 100 bigger than the factor 5 to 20 that we measured for all of these stars. Let's move on to other stars. More massive stars. This is a star that has this beautiful light curve. You see it measured here, and we continue, and we end up here. That's 4 years of data. It's horrible to study stars from the ground that have oscillation frequencies that are now indicated here in cycles per day. Why? This is a big, massive star, a young star, hydrogen burning in the core, and it has oscillation periods of the order of 1 day. So if I do that type of study, which I did for about 10 years from the ground, running to the telescope, observing every night, when I start up, the oscillation cycle is always in the same phase. And you almost observe it as a constant star, no seismic activity, or very hard to determine. So this was made much easier from space data. And here is such a star of a spectral type B. We call it a slowly pulsating B star with this telephone number. And you see here amplitude as a function of period. In this case, it's easier to express the results in period because you expect an equal spacing in periodicity. You see here these dashed lines, they give an equal spacing. Again, there is a pattern, and that helps me to label the modes of the oscillations. And many diagrams here, but just focus on this one. This is a beautiful triplet. It's not a singlet, and that means that this mode is experiencing rotation. And by measuring the splitting, we know how fast rotation is. So again, we can derive patterns and do our forward modeling and deduce that this star has specific properties which are a fine-tuned version of what the basics is. And to give you an idea, here in the upper part you see the measured oscillations, and the black is the measured the measured value, let's say. There is an error bar, but you can't see it because it's 4 years of data and it's so small that it's smaller than the dots. And the green here, the green lines, are the theoretical predictions for a specific model. Not too bad. We're very well onto that. But there are some deviations, like this one here. The green is not where the data is, the red is. So what did we have to do? We had to turn on extra mixing in the interior of the star, of the gas, to explain the seismic data. And so that's what you see in these graphs here. You have here these values of, remember that I had this alpha value for the mixing efficiency. We have been able to tune for this star as a function of the chemical composition of the star. And here you see the observed phenomena of the period spacings. Here you see the error bars now. This is the pattern. It's blown up, so you see how well we can work. The black dots are standard models that we had for a massive star, and they do not fulfill this requirement, but the blue is much better, and we can only get there if we rotate faster or if we mix more efficiently. In another way than rotation, but rotation is the more obvious way. Okay? And so for this star, we then did the same as for the Sun, only we have much less modes. We have 19 modes for this star, which is a big success. After 10 years of measurements for a star like that from the ground, I have 2 modes if I'm lucky. You can't do frequency inversion if you have the difference between 2 numbers, right? It's always easy to solve that. But in this case, we have 19 of these measured quantities. We identify the modes because it's dipole in this case, and we do an inversion of this integral, and then we get the rotation rate in the interior as a function of that. And that's what you see here in this blue line. Still big error bars, but it's the first time we ever did that. And it's kind of a surprise because here is the null line, and it means that this star has some kind of counter rotation in its envelope, and this is not what we had expected. And I can't get that out of my models. So we have work to do. If you have counter rotation, surely you have more mixing. Think of the coffee. And so this is something that we're trying to understand right now. Let me, in the interest of time, speed up a bit. If you have counter rotation, how do you get that? That's not so easy. It means that your angular momentum transport somehow does something weird. And one of the things that can do that is what we call internal gravity waves. This is a star with a bubbling convective core, and it creates wavy structure, and that then transports through the star and carries away angular momentum. And so that changes your rotation pattern, and that you can see in this graph here. I'm going to click, and then you see this rotation frequency that you have at a certain moment in the life of the star. If you allow these waves to transport energy, it changes, and you see how drastically it changes. Our models used to have a flat line as rotation, so that's clearly not what's going on. And so, in terms of the evolution of the star, we now have to revise our stellar models and bring into practice a transport of angular momentum that we ideally deduce from three-dimensional simulations. That's like people who do aerodynamics. It's better to do that in a simulated way, but to do a star in 3D is computationally unfeasible, even with current supercomputers. So we are trying to do localized 3D simulations inside stars. As you see here, this is being computed by an American colleague here. She has access to the NASA computers. I don't, because that's big secrets. That's the military service computers. And then you can do localized 3D computations. And in a localized box in the star where the mixing is supposed to be greatest, you try to export to a 1D description, and that you plug in your 1D stellar evolution code. That's how we are trying to work these days. But this is only a recent evolution, because the plot that I showed of this star is from this year, so it's quite new. A summary: for massive stars that will explode as supernova, we have now these mixing parameters assembled in the past, let's say 10 years, for 13 stars. Let me not go into detail, but that is just to tell you that you typically go at a rate of 1 star per year, even with a space mission and even with a trained team that has all the machinery in place. So this is quite work intensive, working on it. What can we do? We can do archaeology for the people who are more into galaxy structure. This is an area that's, if you want to look at Flanders, is typically more of interest in Ghent. They do galaxy studies. What do these people want? Well, we can offer them ages of stars. That's something that I told you was very difficult, and by tuning seismic activity, we can use these relations between the maximum frequency compared to that of the sun, that is connected immediately to the mass, the radius, and the temperature of the star. So as soon as you measure two quantities, the maximum peak in your seismic diagram and your main pattern, frequency splitting, you can deduce the mass of the star, the radius, and then if you plug that into models, you can deduce an age. And this has been done now for all the red giants. We can do that, and in these different colors you see several 10,000s of red giants in our galaxy, and the green cone here is the thickest one. This is Corot, this is Kepler. And so we can do seismic aging and distances and masses and radii now to a level that is typically a factor 10 better than what you can do if you have no seismic data of these stars. And so this is now helping galactic structure people to do their measurements, to do their modeling, I should say. Then exoplanets, I have to say something about exoplanets. That's really what gives us these space missions, so those big dollars. And as it happens, to find exoplanets, you need to detect tiny little variations in the brightness of the parent star when the planet comes in front of the star. They can have their planets. I want to seismology. That's basically how we collaborate. And that's also why we Europeans got all the NASA data from the Kepler mission. It costed us €0, but they were only after the planets. They want to find Earth number 2, basically. We want to do seismology. So that's convenient and cheap, I would say. Now, as it happens, the planet hunters have realized that the seismic activity of the host star is really annoying for them. It's like the sun, The sun has ppm variations of its quakes, and so if you would be an extraterrestrial somewhere watching us and watching the Earth giving a transit to the sun, it will also give ppm dips in the light of the sun. And these two talk to each other, of course, in the data analysis. So something that has come up and has been realized is, the most interesting planets that we want to find are around solar-type stars. And these solar-type stars, well, they have oscillations. Damn, that's annoying. So we need a space mission dedicated to that. Let me try to round off quickly. Why am I showing that? Because we can now determine the age of that parent star through seismology. And so that's very important, because then we can put our solar system into perspective. And so we can learn something from us by studying seismology of exoplanets also. We are going to do that with Kepler, and it's still ongoing. It was 2 gyroscopes, but it can still measure by a clever operation of the NASA engineers. It now uses the solar wind as its gyroscope to keep it in place. And that works well. We have a factor 10 less precision, but it's still a factor 10 better than what we can do from the ground, and it's uninterrupted. So we have lots of data coming up. You can all download them. They're immediately public to the entire world. So astronomy is one of those fields where we have high competition, because you have to hurry up, because everybody can have the data. In principle, for the nominal mission after 1 year, but for the new mission after already 0 days. That's very interesting. Let me skip this and round off by saying that we are now working on a new mission specifically designed to do asteroseismology and exoplanet hunting together. This is the Plato mission. You may have seen that in the newspaper. It was recently accepted in the ESA program, and we are heavily involved in that. That's nice if you can add to the building of a space mission in your own science topic. We have 10 years to build it. I can tell you this is very short. And so we have our hands busy not only in data analysis of Kepler stars still, but also of the future to find the second Earth. So let me stop here by saying that we are 5 years after our book, and that book was a new field introduction. And in these 5 years we have evolved in precision from parts per thousand to parts per million, thanks to the space missions. From a few objects we had a handful to thousands and thousands of stars where we have data now. We have realized that our models of stellar physics are not good. They are not good enough at all. Nothing to worry about for you. The solar model was already good. We know we can survive for many years, but we are now starting observational probing of angular momentum and interior rotation, and we're having great fun. Thank you.
So, thank you for this wonderful talk. I think this is now open for questions, comments, discussions. And I see one arising there.
I think in the first part of the talk you showed us the Hertzsprung-Russell diagram with the stability areas.
Yes?
Outside of those areas, are there no oscillations, or are they too small to observe, and why?
Probably, and they are, everybody in nature oscillates, you know. If I slam on you, you also oscillate, but you damn quickly, depending on how hard I hit you. And so, that's the way to think of it. There are oscillations probably everywhere in this whole, in every star, as in every body, but if they are not self-driven, then they damp out quickly and we don't observe them. We see these stars as constant. Now, of course, when I say we see these stars as constant, that's up to our current threshold in the data precision, which is parts per million. Okay? So, if I compare the diagram that we have now with the one prior to Corot and Kepler, it would be new pulsating stars, because parts per thousand we can do from the ground. Now we move to parts per million, and we all of a sudden see very many stars which we thought were constant that have seismic activity. So probably if you would go even further, you would also still see lower amplitudes. So it's a matter of amplitudes, and it's a matter of, I could call it mode lifetimes, if they damp out.
I think 40 years ago we couldn't have imagined that you would have brought us such a lecture like today. And so I want to ask you, it probably will be one question. If you would penetrate deeper into the stars, you would then see that there's a lot of activity over there. Would you say on the surface, you would say there are so many dead stars, but deep down there's still liveliness, or would you say no, it's from another point of view, you would say they are pretty dead as well compared to other?
That depends on how you define dead. Because end products of stars like the Sun is what we call white dwarfs, and they are dead in the sense that they have no nuclear fusion anymore. They are just cooled off big diamonds, basically. They're carbon-oxygen balls. They have a tiny little layer of helium and hydrogen, but they are too cool to do, carbon burning. You require really very high temperature, and they don't get there. That's a quantum mechanical effect, and that's a whole lecture by itself, but it comes down that in all these nuclear fusion cycles, each time the star has to make itself hotter to do the next burning cycle. And each, as you go in your chemical table of elements, you always have a higher requirement on the temperature. And it depends on how high the star can get, where it stops in its cycles. But so these dead stars, they still have seismic activity. We measure their seismic quakes. So white dwarfs, they have oscillations. And so we still study even those phases. What we would ideally like to do is do seismic studies of black holes, of course. That would interest the physics audience. But we can't for the moment. But this will come. This will come because black holes also have seismic activity. Neutron stars are in between. And there we already see some quasi-periodic oscillations. But these objects, they do have a very strong magnetic field also, so there are a whole lot of complications. But they radiate in X-rays, even gamma rays, so we can't do it with visual instruments. So it's also a matter of wavelength. You have to build a specific space mission for that. But if we would have money, we would do that. And in fact, the slots that is taken up by Plato, which is a mission I'm heavily involved in, so I'm very happy we got prize #1. But the second one was a mission to do neutron star timings. And that wasn't chosen. It will come back. That's the way the space agency works. And then we could do that. So bottom line, dead stars have magnificent seismic activity. Okay.
What drives the quakes on Earth is plate tectonics, but what slaps the star?
Yes, good question. It's obvious question. That's a whole lecture by itself. But it depends on the type of star. Like the Sun has an outer convective layer and an inner region where the created energy is transported by diffusion of photons. So we call that a radiative region, and on top of that is a convective region. So this convective region, that's like the boiling kettle. The surface layer of the water has quakes. That's similar for all stars that have an outer convective layer, right? So all these red giants are like that. So I call them solar-like quakes. The more massive stars, like the one with this counter-rotating layer, is different. That is, in fact, a long time ago in this university, I learned about the Carnot cycle in thermodynamics, right? You all know that. This star does that. And so there's a layer inside the star somewhere at an idealized position where that layer is partially ionized. So it's a mixture of atomic elements that are neutral versus ones ionized, say. And then there's a whole bunch of radiation coming from the core, from the nuclear reactor, and these photons are absorbed and are used to make the layer homogeneous in terms of ionization degree. And that is able to pump up the star, basically. So that's what we call a self-driven oscillation. And then you have a third way to invoke quakes that you know very well, because the moon does it to us every day. You have tidally excited oscillations. So we have plenty of binary stars, also thanks to this mission. Two stars are revolving around each other, either in eccentric or circular orbits, where the tides induce oscillations. And they are of a very specific characteristic nature, but they are there and we detect them. So basically 3 ways to excite oscillations that we know of today.
So there's not an epicenter somewhere at the surface?
No, no.
You said that discovering exoplanets is influenced by the seismology of the stars, but I'm assuming then that it also works the other way around, that objects moving in front of the star influences the measurement of the seismology.
Yes, that's what we call eclipse mapping. That's beautiful.
How do you know then whether or not you're looking at a star that's pulsating, or if you're looking at a star that's being blocked by a bunch of junk that just happens to move past it?
That we see infrequent. That's the beauty of Fourier analysis. Because the quakes are periodic phenomena, nice science, very stable periodicity. A planet that moves in front of a star has typically a transiting period, you can do that with Mercury or Venus if you like, of several hours. So we can unravel that unless the period of the quakes is several hours. And then it's really hard. But a planet blocks light in a specific area on the surface, so we can still unravel that. Let's say there would be rubbish floating around the star, it would be not so strictly periodic. And in frequency space, in the Fourier spectrum, it would give a rising, steep power at low frequency, because it's not coherent. And that's the way we unravel these two. But it's true that they are mixed, and for some stars with some type of planets, in some type of Kepler orbits, we are unlucky and we have a hard time. And that is even excluding, because I didn't discuss that today, I already had too much, even excluding variability due to magnetic activity, because that also gives rise to fluctuations. Complicated, but we can manage.
I see 2 more questions, so I think we should either of you go.
Okay. Could you use then seismology to detect the planets?
We do that. Yes. Transiting time variation. If you have a good seismic model, if your forward modeling performs well, and you have this agreement that I showed in one of the slides between these green and measured frequencies, then we can indeed do the reverse, and we can say, okay, now we understand the seismic behavior of the star, we can extrapolate across the whole time series, and we see some deviations where it doesn't really fit very well. Then there must be a cause why it doesn't fit. And a planet cause goes with an orbital period. So an observed minus computed time series will then point towards planets. And we have several planets proposed in that way, but of course, ideally you also want to have an independent confirmation that this is what's going on, instead of your seismic model not being good enough. That's always the difficulty in these cases. In some cases, if the star is bright enough, we go and do spectroscopic velocity measurements from the ground to confirm. But sometimes we can't do that because the object is too faint. But yes, we are doing that.
So it's maybe a simple question, but for the string I know why I have equidistant peaks in the spectrum.
Yeah.
For a spherical object like an atom, I have a Balmer series or so with not equidistant peaks.
Right.
So this must be some linear propagation along the surface or so?
Yes, but it's because we are at very high frequency that if you, in general, I talked about these mixed modes. In practice, you always have the pressure force and buoyancy acting together. That's just the way it is. But in some cases, you can ignore one of the two restoring forces. And then you enter in a very simplified regime where you are almost equidistant, but it's not. I mean, I told equidistant, but it's not. So in practice, we see deviations, and we have to, as you say, because else you would not have a physical system that would be connected to the real stellar gas. So we have deviations from equidistant spacings, either in period or in frequency. And these departures, in fact, tell us how the density is distributed inside the star. Yeah.
So I saw a few more questions, but I think it's time to round up. So I invite those people who still have questions to talk to Professor Aerts during the receptions and let those questions be the ground for healthy discussion. With that, I think we should thank our speaker one last time. Thank you very much for giving us.
With pleasure, and I didn't get this when I graduated. You made up for it now.
So with that, so again, allow me to remind you for the 20th of February, where Kouwenhofer will be in lecture, and the 31st of March, when Professor Halden will come to give a talk. And then I will invite you all to